Good day, folks. I was observing some effects I was noticing on the scope while I was testing simple, as you see in the demonstration, some LC circuits being fed with regular AC. And I noticed something really, which seemed to basically be a glitch on the scope. So then I started researching about it, and sure enough, apparently it's not a glitch. And we always wonder how to take advantage of this reactive VAR and convert it to real power, because that's usually the problem, right? We see that these reactive gains usually in traditional setups as a kind of ghostly energy that we can't really utilize, right? Reactive power is not real power. In other words, it's not active power, and we need active power, right? But there are some clever ways, as we've talked about in previous videos, of trying to tap in and convert some of that reactive power back to real power. So depending on mechanisms and methods, in theory, there are possibilities, but it can get quite complex. So let me explain here what happens at high frequency RF, and I will explain why later it has to be with RF. So for my example here, I'm using 4K, I call it RF, okay? Just a 5 volts 40 mA trigger here, AC, going to a 2N capacitor and an 80 mH inducer. So ironically, these values happen to resonate very close to 4K, something around 3.96. I may be wrong there, I'm just doing it real quick, but it's around there, okay? So you're basically resonant with the circuit. So what's going to happen when we feed it regular AC and you zoom into your scope at that resolution, you're going to see your normal high frequency waveforms as an AC sort of RF frequency. So it's going to, I'm a bad drawer, but this is how the waveform will look like when, even at 4K, when you're at the proper resolution here. Okay? But what happens through the action of resonance is we get the resonant amplification. But the extra voltage, especially in our Joule Thief circuits and stuff like that, it doesn't, like when you, let's say we read 500 volts, it doesn't mean that you're steadily pulsing at 500 volts. It means that the oscillations are accumulative and reaching that. It's like pushing a swing. You start with a small trigger, the swing rises up, it comes back down, then you give it the same push, which is our input, then it makes its way a little further, you give it another push, it makes its way a little further, and then finally it plateaus. You see what I'm trying to say here? It needs to build that up. So essentially, if you start zooming out, this would be like the equivalent of a zoom out. The orange would be the current, and the blue would be, sorry, the orange is the voltage. Here I have 7 volts plus and minus 700 minus. And then in the middle, the blue here, it's hard with my drawing, but that would be the current, which slightly follows the voltage because of the phase variant with the reactive going on here with the LC circuit. So once you zoom in, you end up seeing something like this. But what's very interesting is your 5 volt starts here, and then resonance kicks in right away. Your next pulse might be 15 volts, and then it quickly rises, like I said, that swinging actions, and then it'll plateau. And then what happens, I actually simulated this to see what was going on, and then it'll ping pong like that from one system to another, and then it plateaus and then starts to go down as the other one starts to go up within the circuit. But total, if you put a probe on here, you get this kind of up and down, the amplitudes as the cycle switches back and forth with the resonance, the ping-ponging, okay? Now that's nice and everything, but I've noticed that as I started zooming out more, folks, I lost the resolution, and all of a sudden it would be like coloring this in, like hit this, and then you would color all of the inside here. This is the current, and then this would be all solid in here because we're zoomed out so much we don't see the 4K. I think you're going to get that aha in just a moment here. So in normal reactive power, the current is out of phase with the voltage, and that's why it's very difficult to make use of the reactive gains, because the phase variant, right? So now we have this, and the same thing happens with our voltage here. All of a sudden, you get this thing here going on. You got this thing like that. And then when we color that in, this is once we've zoomed out a lot. This is still going on at 4K, folks, but it's just we're zooming out so far that we're not seeing the individual 4K pulses no more. So once we've colored it all in, I think the aha moment is starting to come here. All right. So now we're pulsing at 4K, we're getting amplification through resonance. And once we're zoomed out, we get something like this. Now, what this is considered, folks, here is the envelope of the total waveform energy distribution. So this obviously repeats. So now you can picture a much slower waveform here going on, a real sine wave. Okay, sorry folks, my apologies for that. My camera ran out of space, so I had to chop the video. So as I was saying, this goes on here, but with the envelope we get what appears to be a much slower waveform here happening like this. But what's very interesting is it's happening now, as you zoom out, at the same time as the positive and negative. So essentially you're getting what appears to be a regular, closer to 60 Hertz AC sine wave once you've zoomed out, but it's also happening at the same time on the negative side. But what's interesting is now it appears that the current is back in phase at the lower frequency. So we're offsetting it back, you know what I'm saying, which is very great. And not just that, but we're getting the output of the resonance amplification on each side of the polarity. But it sounds too good to be true, probably because it is, folks. And for a moment, I'm just going to have to burst your bubble, because you're probably thinking, oh great, he's figuratively solved it and this is going to save the world. And no. There's a catch, unfortunately. And you may have noticed what we're getting here is the equivalent. Okay, so it might be near 60 Hertz. And this is why I say it has to be RF and high frequency. Because in order to get this slow envelope effect as the resonance ping-pongs back and forth between the LC circuit here, this happens a lot slower, as you can see. This will happen at any frequency, but the time may be so slow that this wave might be like 1 or 2 Hertz. It's not really fast enough to make it applicable. But once you get into the very high frequencies, this envelope here becomes a very compatible waveform. So again, what I said, there are some issues. You can't just use it like that. It just appears that it's filled in, but it's not. We still have all our 4K here. So just like Don Smith would do, simple capacitor filter could keep that exactly like that on the output. So that's solved. But we have another issue. What's this going on here? We've got a phase variant of 180 degrees here. So what happens if we try to rectify this? We're going to get near zero. Darn. So here we were so close to finally being able to take advantage of this reactive gain, only to find out, darn. Well, I started thinking about it. And then it came to me, you know what? Simple solution. Half bridge rectifier on this side, half bridge rectifier on that side. Each of them will catch the positive, but even though it's just by the alignment, it'll see the negative, it'll convert it back to a positive and knock out, even though if it's 180 degree, it'll filter it out. So it'll catch just one side at a time. You put it on each side. So what do we do with this? We send it to a center tap transformer where we have one side of the plus that goes on this side, the other side of the plus, and then the common ground here. So that combines our positive spike at the same time on each side of the transformer, so that on our secondary here we convert it back down to, let's say, 110 volts. So here's a 110 volts, sorry, here, 110 volts AC output, essentially. There you go, a little bit of capacitors to filter this out, and we've taken advantage of the reactive gains, and at slower frequency with some filtering, we're able to bring the phase back in and take advantage of the high current, the amplification, and even utilize the out of phase signal. So just another method I wanted to throw out there, folks, and just talk about. Food for thought, and I hope you enjoy, and I'm always looking forward to the comments. Thank you all.